the light of the microphone is on.
Yep.
And we all know Leonid.
Yes.
Next lecture,
Okay.
please.
I have to say several words to finish this part, this section that we call the wide theory. The one point is that there is very important relation that I'm going to use, and it comes just from if you'll do all these things that I just outlined it explicitly, you'll find very nice formula that I will need later, therefore I write the formula. You take the spectral measure, which in fact determines everything about the Schrödinger operator on the semi-axis, and you integrate. There is a parameter alpha which varies between 0 and pi, and I integrate, and the result is, excuse me, just the back measure. I repeat it, it comes immediately if you do things explicitly. It's very useful identity. So it doesn't matter what is the potential, it is always valid. Let me even make a special reference for this formula because I'm going to use it to prove localization. And one and second, to finish, I remind you that I explained to you how to construct the starting from the operator on the finite interval, how to construct the operator on the semi-axis. Now, I would like just to say a few words about the operator on the whole axis. The situation is simple. You start, as I said.
Dennis, just maybe could you give a few comments on this form? Because
Yes.
for me it's at least not obvious. Maybe it's obvious.
No, it's not obvious. No, you have to. Okay, if you do all these constructions that I said, you have to, in fact, you have to analyze the equation for the eigenvalues because it's even valid for the finite interval.
Should
So-
there be a 1 over pi?
Huh?
1 over pi?
No, like that.
Not average, just integration.
I integrate about the boundary conditions.
Very non-obvious thing.
Okay, it is.
I would have thought you must put 1 over pi. So.
No, not necessarily, no. Okay. Now, what about the whole line? You just do the same, but you remember what did I do? I wrote at the beginning. I wrote the operator on the finite interval between a and b, and starting to work with semi-axis, I put a equals 0. Now I didn't do this. I just take this interval a plus 1. So how do we do it? Minus infinity, of course. But I take the interval which, roughly speaking, contains 0 somewhere in between, because I'm going now to to send to b to plus infinity, a to minus infinity.
Sorry, can I just ask, what happens if you do this on a finite interval and you still have the beta? Is it still true?
Sorry?
With your first formula, the one which you integrate the alpha,
No,
not true if you
No.
have beta still.
no. No, it's true.
It's true.
It's true.
Ah.
Yes, it's true.
So
I
even for
repeat,
finite
just
pieces.
roughly speaking, you have to do the following. You have to play with derivatives. Write the equation for eigenvalues in the finite interval, and make the derivative of eigenvalues with respect to alpha. And then you will find some simple formula. And then use the definition of rho, because it contains alphas. What is rho? Or the finite interval? Rho prime. Yes, rho plus, as I wrote, rho alpha beta AB on delta. Let me write the formal derivative. The density is just the sum lambda minus lambda L, and lambda depends on everything, on alpha, beta, AB. And now you write the normalization factor. All of them depends on alpha. If you carefully differentiate and then integrate, you'll see that this will come out. In fact, it is known, I think, in 19th century, but it was not explicit. I think Lord Kelvin knew the formula already. Therefore, it's quite old, but it's very useful. I will not prove the formula because it will be just a. I will need it to, we have to prove localization of the whole axis. But it is a bit hard and not evident how to do if you just start from the zero. So better to make as a warm-up the same for the semi-axis, just for the pedagogical purposes. And in that warm-up proof, I'll use the formula. If it would be principal for the whole axis, I would prove, but since it takes some time. Okay, what about the axis? You remember how did we construct the eigenfunctions, the generalized eigenfunctions for the semi-axis? We worked with Cauchy solutions. We renormalized our, we constructed our eigenfunctions via Cauchy solutions and then singled out the normalization factors, putting them all, accumulating them in row. Yeah? Now you do more or less the same. But you need now, you have your eigenfunctions. So you do the same. You start from the left corners, left end, A plus 1. You finish here. But since now you are going to send this to the infinite right, to infinite left, so you fix boundary conditions not on the left end, but somewhere in between, say at 0. And now you need two solutions. To express any solution of the second order equation, you need two linearly independent solutions. Tradition is the following. We used to take two solutions, y0 and y pi over 2. The first one, y0, yes, on this will be what? It will be 0 at 0 and 1 at 1. So sometimes it's called S solutions because it's like sine.
What is 1 here?
I am on discrete axis. Yeah, but in the second solution, I do the opposite. This is 0, 1, sorry. No, it is, yeah, right. You're right, Jan, excuse me. Pi over 2, 1, lambda is, it's like cosine solution. Cos solution. It's like S solution, sine solution. They are linearly independent, and you can express any solution via these two solutions. And now you work more or less the same. But now you will have not just one normalization factor, but in fact 4 for the square of this, for the square of this, and for the somehow for the cross terms. So you repeat basically your result, and you'll get eventually the same result with the measure. Now your measure doesn't depend neither alpha nor beta. We have a boundary condition here. It is alpha, it's beta. Your measure doesn't, if the operator self-adjoint, your measure doesn't depend neither on alpha nor on beta, and you'll get certain spectral measure for the whole axis. It could be, in fact, it could be chosen by differently. There are many ways, but there is very simple formula, not efficient but quite useful. You just write you can take, it's a kind of cheating because this is what I'm going to construct, but you construct something which does look very nice. But then you recognize that your construction is here. So you get your result. By the way, why it is more complicated? Just technically more complicated, but there is a more deep reason. The problem is that if you on the whole axis, your spectrum is multiplicity 2. And what does it mean? That for any value of spectral parameter in the spectrum of lambda, you have two solutions, two eigenfunctions. Unlike semi-axis when you have one. And just to show you that it is like that, let me let me give you an example. Just this one, the Laplacian in L2Z. Okay, it's simple thing. Just okay, I don't know, Laplacian delta. You have just 0. Okay. Now I have to write the double infinite matrix, yes? Because my index is now from minus infinity to plus infinity. If it is 0, so here will be plus infinity, here will be minus infinity. And I write here 1, 1, 0, and then everywhere, and zeros. So it is just, if you write the corresponding equation, it will be, the operator is given is by this equation, correspond to this equation. And you can easily solve this equation just by Fourier transform. You just write psi x 1 over square root of pi e to the a e. Let me use the physics notation. I write the momentum or quasi-momentum here is the same. And my lambda is, before I wrote theta, now I write in. And k here is from 0, better write in this way, 0 to pi. But the spectrum, you see that you take k minus k, okay, oh, better like that. It's more symmetric, minus pi, pi. So you see, you take k minus k, lambda will be the same, but these functions will be not the same. So you have two eigenfunctions for both generalized because they do not belong to L2 on the just exponents. And in fact, this system is complete. We need not spectral theory. We know from the Fourier analysis that the system of exponents is complete in L2. This is called Plancherel theorem. So everything is okay. This is spectral, complete spectral analysis. These are, well, you can use either for any lambda. Now you have, as quantum mechanics people used to say, we have degeneration. We have to say that, okay, there is a parity, new operator here. So you write, you have, if you would like to write complete labeling, you write 2 pi. 2 pi e to the plus minus ekx. And in that case, there will be one-to-one correspondence between k, now my k here already from 0 pi, and I have one-to-one correspondence between lambdas and k's. So now I wrote explicitly the fact that my spectrum is of multiplicity 2, despite that eigenfunctions do not belong to the space. Or instead of that functions, it's maybe not too good because everything that I did for the semi-axis, and as you can find in any book, there is a classical book by Titchmarsh, volume 1, where everything is done. It works except only with real solutions. So you, instead of that, you can write 1 over 2 over pi cosine kx and 2 over pi sine kx. And you'll get just Fourier series written not via exponents, but via cosines and sines. But nevertheless, you have two linearly independent solutions. Both of them are generalized eigenfunctions, bounded. In this case, not growing at most a square root, but bounded. And this is complete spectral analysis in complete correspondence with that. And if you compute this measure, this will be a gain. Rho h d lambda is the gain So we have, I repeat, for the whole axis, we have, roughly speaking, double amount of objects. We have modulo this condition, everything is the same. If you take, for example, instead of Jacobi matrix, something more general, if you take, you see here, I take the matrix that only, here just two diagonals contain something non-zero. If I would write the random Schrodinger, I would have to put here the potential. In principle, and as far as I understand it, it will be quite thoroughly discussed in the Untitled Chapter lectures. We can study more general case. We can write, just take a band on a strip of finite width, and inside some coefficients outside zeros. This is, in physical terms, it is just, you study the oscillation of strings not only with nearest neighbors, but with a finite number of neighbors. But in that case, there are analogs of these objects, but in that case, you have to choose as many solutions as the width of the strip, but nevertheless, it's finite things. Therefore, you will just work with some finite dimensional vectors, measures, etc. Okay, this is what I would like to say. And there is the same statement. So we have a spectral measure. We have spectral theorem, but in that spectral theorem, you will have now, let me write.
Let me ask one thing.
I'll finish. I'll write the spectral theorem and then I'll answer your question. So I have as a H, this is Schrodinger operator. Now x prime delta is now sum over sigma equals 0 pi over 2. Here I have to write certain functions. Okay, y alpha x lambda, y alpha, not alpha, sigma prime, sigma x prime lambda. Here we have certain measures, sigma prime d lambda. We have a 2 by 2 matrix measure. So this is a measure, but with values 2 by 2 matrices. And the measures that I wrote, it is just 1 over 2. The trace of this, just one, okay, better to write sigma, 0 pi over 2, rho, sigma.
So I just wanted to ask, you are illustrating or explaining the multiplicity 2
Yeah.
property.
Yes.
And the example of the Laplacian without potential.
Yes.
But it's still true.
It depends. If you take, for example, pure point spectrum, it is of multiplicity 1. In general case, if you have a arbitrary, you have a Schrodinger equation on the whole line with arbitrary potential, it could happen a lot. For example, if you take, let me remind you the case of the electron in a constant electrical field. Potential is just x. There you have the absolutely continuous spectrum by multiplicity 1, because the particles can't go to the plus infinity. So it could happen, okay, anything is possible in that frameworks. The spectrum could be multiplicity 1. Though we know for sure that the point spectrum is multiplicity 1. Why? It's answer on your question. Because let's write Wronskian. So if you have, assume that we have two bound states, two eigenfunctions for the same eigenvalue, but genuine eigenvalues. That means the eigenfunctions are over 2. That means that they decay. We do not know how fast, but we know that the integral of squares, the series of squares converges. Yeah. Now, if you have two solutions corresponding of your equation, of this equation with potential, corresponding to the same value of spectral parameter, then okay, so you will have the formula. You have two solutions, yes?
The Wronskian is constant.
Yeah, it is discrete analog of the Wronskian. Sometimes I was told by some people who like history of mathematics, that it was written by some Italian mathematician in 19th century whose name is Casorati. So to give it justice, it's Casoratian, but it's not nice. So it is a constant. It doesn't depend on x. Now assume that you have two solutions. So you send both to x infinity and you get that constant is 0. That means that they are linearly dependent. So you have no. For the pure points, for the point spectrum you have no. For the absolutely continuous spectrum, if potential is decaying in both directions, you have scattering theory. Absolutely continuous spectrum is multiplicity 2, like for the free Laplacian. But in this example that I gave you about the electrical field, continuous case, but there are examples corresponding here. In that case, you have absolutely continuous spectrum by multiplicity 1. Because if you go to one direction, you have a standing wave. Yes? But in another direction, you have decay, exponential decay. So it will be absolutely continuous spectrum multiplicity 1. But in spectral, in random Schrodinger, we have always, we have complete localization in one-dimensional case. That means that we have always the spectrum multiplicity 1. But in general, as this simplest possible example shows, you can have 2. Why not? Okay, this is the end of the wide theory. And now let me pass to the next chapter. Now we are closer to so there is nice formula. Since I wrote some title, in this title contains some words, I have to explain these words. I explained to you what is operator, what is self-adjoint. Now my goal is to explain what is ergodic. So the first section will be just, let me call elements of probability and ergodic theory. It is just more than elementary, just few notions that I'll need. Okay, the first point is the notion of probability space. Probability space is a triple. This is a certain set. It's called, the space, probability space, just a set. Here you have a certain collection of sets that are allowed in your theory, called sigma algebra of events. So it's sigma algebra of events. Yes? I'll give you a simple, and here you have a measure. That means that for any set from sigma algebra, you prescribe a certain non-negative number. So if I have a set from sigma algebra, I can always compute. I have a prescription how to compute a number which is between 0 and 1. In particular, the probability, I'll write in this way, in curly brackets. The probability of total mass is 1 is just normalization. And as I said, it is sigma algebra. That means that if you have a set AL, all of them from F, then the probability of the union is sum of probabilities provided that sets are pairwise disjoint.
Excuse me, do you mean A is subset of F or A is element of F?
No, it's element. If it would, A is a subset of omega, but but you have you take omega, it's just points, yeah. Then you say that I am going to consider a certain collection of subsets of omega. Each subset is a member of this algebra. Standard things, I'm explaining in fact the so-called the back construction of the integration theory. In the standard, the simplest possible case, let me give you as omega is just 0, 1. Now, the sigma algebra here is called Borel algebra because it was first constructed by Borel. How does it go? You start from intervals, say semi-closed intervals. You start from intervals A, B, all B, all endpoints are from 0, 1. So you start from all intervals inside 0, 1. Now you make any unions and any intersections. But very important point, not only infinite numbers, but infinite numbers also is possible. And this is called Borel sigma algebra. And now you define the measure just dx. But now it's not Riemann, but the back. But maybe difference too subtle. Just a scheme, yeah? But in probability theory, we take not necessarily 0, 1, but any set on which this construction is possible.
And why is this an algebra?
Huh?
Why is this an algebra?
Yeah, it's because I can think of these in terms of their characteristic functions. The characteristic
You can multiply them, yeah.
Multiply.
Yes.
This is why the algebra.
You can take all products and sums. Okay, so this is probability space. Next notion, I need a notion of, I repeat, okay, by the way, in 30s there was big discussion mostly between Kolmogorov and Mises. Because Mises said probability theory doesn't exist. It is just a small part of measure theory. In fact, of course, he was right. Kolmogorov was not so negative with respect to Mises, but he said, you know, if you are working in measure theory, you do not care about special class of spaces called product spaces that I'm going to show you. And it corresponds to independent random variables. So for general measure theorists, to consider the product space, it's a kind of trivial exercise. But all the probability theory somehow is based on that special case. Okay, and for example, in Moscow in 30s, the teacher of Kolmogorov was Professor Luzin, very well-known specialist in function theory and integration theory. And Kolmogorov, by the way, was his student. And I read once the letters that Luzin wrote to Kolmogorov, because Kolmogorov, it is him who invented this axiomatic, but he proved enormous amount of very strong concrete results. And Luzin wrote him a letter saying, you are absolutely superb mathematician. Why you are working on this dirty part of the theory? Okay. Now, so next notion is the random variable. It's very simple. It's just measurable functions psi omega 2 r. Just to have a function, define it on that space. What is measurable? Okay, maybe it's too subtle. Don't concentrate on that. You have just a function, define it on the space of omega, and this is random variable. Yeah. I need several notions. I say that psi is not random excuse me for triviality, that means that psi is constant p almost everywhere. Yeah? If you have a constant function, it is not random variable because it does fluctuate. But I will use this notion quite often. And the next thing that a set, okay, don't bother about a set of R, say delta, is not random means that its indicator K delta is not random because we will be dealing with the random sets. Therefore, okay, sets, it's a bit tricky thing. So it identified a set with its with its indicator. What is indicator? If you have a set, okay, just what is indicator? It is just a function that takes two values. It is, what is it? It is 1 if your variable is from delta 0 otherwise. Yes? But now, if set is random, that means this function is random, and I said that set is not random if its indicator is not random. Just to reduce one thing to another. And one more thing I'll need, everybody knows, I need the notion of expectation. Expectation, which will denote by E of a random variable. This is nothing, just integral of this function psi over the space omega with the given measure p. Well,
There is a question.
yes.
Maybe you should write omega instead of r for your indicator function, the function from omega.
No. You see, David, I have a set on the real axis.
Oh, I see. So your omega is.
Yes, so you can make the one-to-one correspondence between sets and characteristic functions. Excuse me, indicators. And then, okay, if set is random, that means that this function is random, etc., etc. Just to reduce, because sets are less, I know. Okay, this is just a reminder of basic things. And now I'm going to consider an automorphism just a transformation, any transformation, transformation omega in itself, and it will be just, I know, endomorphism, but I assume that it is invertible. This is why automorphism. So you can, there is inversion of this automorphism. Yes? Then we say that T is measure preserving if there are two properties. First, for if for all A from my sigma algebra, TA is again in integral sigma algebra, and the probability this is the same. This is why the title, Measure Preserving Transformation. Yeah? And this is, of course, okay, for all A. Yes? And now I need the notion, the invariant set of omega. In fact, of f. What is it? Invariant set, it is a set such that TA equal A, but not necessarily precisely as two sets point by point, but just you take a set, you make its transformation, you have a new set. If their measures, if they coincide, modulus small amount of measure 0, we say that we have the invariant set. So ideal case when they coincide, but not necessarily. I just would like to say that this thing will be everywhere, and in fact it is everywhere in probability theory. It is just, I would say, the rate of precision probability theory. Probability theory can say nothing about the events of measure 0, yeah? It's by definition. Despite that this set could be quite massive. In this simple example about with interval 0, 1, all rational numbers, their measure is 0, but you know they are dense. Okay. So this is invariant set, and now I can define. I need also the notion of invariant random variable. Okay, it is clear what is it. It is the variable xi omega. So you have the function in that point coincide for almost everywhere, yes? So they, in principle, could not coincide on the set of p measure 0. This is allowed. And now, having this notion of invariant set, I can define the basic notion, which is called ergodic automorphism. Yeah? Before we had measure preserving, now ergodic automorphism is the form. The only invariant sets are omega and empty. So there are no parts that could, there are no parts of positive p measure that t could bring it in themselves. And in that example that I showed, it is just if you take, now you replace 0, 1. Okay, in fact, this is view 0, 1 as a one-dimensional, as a circle of unit length. Yes? Therefore, identify 0 and 1. Nothing, with respect to measure, nothing will change. It will be the same. The back measure on the interval 0, 1, and etc. They will be the same sigma algebra and the same everything. But now I define the rotation of the circle by the angle alpha. For any alpha, doesn't matter what is alpha. Of course, you have to write this relation. That means that I have to take fractional part of that, yes? And for any alpha, this is measure preserving transformation. We know that from, if you make any rotation, the measure will not change. But if alpha is irrational, this will be ergodic transformation, because you can't make it will never be the same. Yes? How you can bring this? Take, for example, first alpha rational, then doing, let alpha is p over q. Both p, q are integers, yeah? And q is positive, of course. Then, if you apply this transformation q times, and any set will coincide with itself after q rotations, yeah? Maybe even less, but q for sure. But if I take alpha irrational, I will never obtain the same. Doesn't matter how much times I will apply this, yes? So this is ergodic transformation if alpha is rational. Well, let me.
I'm a little confused because invariant set is defined by applying T once, but now at the bottom of it, you now have in mind that T can be applied.
But you can take any power. You can take any power and to do the same, and you'll get that. Okay, maybe you're right. I have to write here T to the power, but just a moment. Maybe it is better to. No, it's the same.
So when you define an ergodic automorphism, invariance means invariant under the
Repetitive
under sort of the dynamics.
Is it necessary? Just
Take all points and rotate it just once, and then you back to all Q points. And you have an invariant set.
okay. In fact, it is not necessarily, but maybe just to be not to discuss too much. Let me assume that assume that Tx x from Z. So any power. In fact, it is not necessary, but it's a bit more. Okay, and now we come to the notion which we will need: abstract, dynamical, system. It is just a probability triple plus all powers of T. So you have 4 objects in that. Probability space, sigma algebra of events, the probability measure, and then you have a family of these transformations, just powers. And this is additional element of this structure. And now we say that dynamical system is, say, measure preserving if T is measure preserving, and if it is ergodic, if T is ergodic. And one more thing. Now I need the notion of the homogeneous random process.
So to understand it, the randomness is for the dynamical system is only in the initial conditions, or the transformation is also random?
No, only in initial conditions. Because my measure on the omegas, you see, the formula is measure is here on omegas. There is no omega inside T. It will be an additional thing, yeah. Homogeneous random process. So it is a function. I will denote V because in subsequent it will be our potential. This is the function of space special variable, in our case just of integer, and the so we have to write Vx omega. This is just random process. Any function of 2 variables, of some special variables and of the random variables is just a random process, but the homogeneous process has a special property. So we have a property that x t a omega is Vx plus omega. So, and I assume that T is measure preserving. So I take measure preserving transformation. So not any function is a homogeneous, not any random process is a homogeneous random process. It has to have this, you see this property. Application here is equivalent just to shift. and just a
For any
yes, yes, for all A and X and omega, for all things, etc. here. And just a second of reflection shows that you can write the process as so the construction, abstract construction on a homogeneous process is very simple. You have abstract dynamical system with a measure preserving T. Now take any function, any random variable, and put here this. Because we know on omega some random variable. You take the random variable and you just introduce the argument as a degree of your transformation. So it is a general construction. In fact, I proved the theorem, which is almost evident that the homogeneous random process is a function. A random process is homogeneous random process if and only if it could be written in that form. Because if it is homogeneous, it's immediate, and converse is also immediate. And the same for ergodic random process. So the same construction, the same formula, but with ergodic T instead of measure preserving. It's very nice, but how to check? Because usually in applications, they give you a process, how to check that process is homogeneous or ergodic. You do not know usually what is T, what is transformation T. You know just random function, but what does it mean to know a random function? And this will be last point of this introduction, how to check. Yes? Okay. Introduce special things. Introduce cylinders. So you take a set of omegas where x1 omega belong to certain interval, etc. Where xp omega belong to a certain interval delta p. So this is an element of sigma algebra, just an event. You are considering the event in V. You take points. You take a collection of points, all from your space. And now you take these points. Since you have chosen the point, it's just a random variable. You can ask a question, what is the probability for this random variable to be such that values of random variable belongs to a given interval? This is a ordinate. Yeah? So people used to do the following. Just there is a picture. This is P. You write vertical line, you do delta. Delta 1, delta P. You do some gates. And you require that your function will pass all the gates. And you ask what is the probability of this random function to pass all the gates that you established. These are cylinders. It's called cylinders. Why cylinders? Because you fix only finite number of x's, and with respect to all other x's, you ask nothing. And now you introduce a family of just joint probability of this event. So it is just probability of this event. So you have, what is it? With respect to delta 1, delta p, this is just probability measure, but multidimensional one, because joint probability distribution, yeah? And we have these points as a parameters. So you have a family. So if you have a family for all, now you choose this for all collections of x1, etc., xp, all p from Z, and all, in fact, Borelian sets. So you do all possible, you ask all possible questions about how does your random function behaves, how does it pass any possible gates that you do for this function, yeah? So, and there is a famous theorem by Kolmogorov that under very mild conditions says that this family of all possible cylinder probabilities determined uniquely the process. It's more or less intuitively clear, but it could be proven. Yeah, and now, so it is more or less equivalent description, but it is what is given usually in practice. For example, on David lectures we had a Gaussian process. Yeah, Gaussian process you have to have positive definite matrix, which is a correlation matrix, and then you write probability for any number of phi's, for any collection of x's that was in David lectures. So it was just, in fact, on my language, it was just the all possible cylinder probability for this field that was defined on the lattice, Gaussian field. By the way, what is it? Why I say processes and David said fields? Because this is just historically. Process, it's one-dimensional function. X is one-dimensional. If all this construction could be done in many dimensions, on any ZD. In that case, by historically, people say this is a field. Field is function that depends on more than one spatial variable. Yeah. Now, it turns out, it's simple, almost evident, but the corresponding. What is the homogeneity of your process? Probability, all these cylinder probabilities should be invariant with respect to this shift, any shift. It's clear from the definition. Okay, in one direction it's evident, in other you have to work a bit. So I repeat, your process is homogeneous if and only if all cylinder probabilities are translation invariant with respect to these parameters, to these x's that are parameters of the distribution. This is why physicists used to call this the probability, the translation invariance in the mean. Because if you look on the realization, of course, the realization corresponding to these two, the part of this function here and to the shifted part could be completely different. So if you look just on the trajectory or just one fixed omega, you look at the function, it will be completely different here in those points and in shifted points. But the probability will be the same. So we say that this translation invariance in the mean. So this is the homogeneity, and the ergodicity is a bit more tricky. Let me be not too precise, but simple, yeah? Just you write that x1, etc., x, say, p1. Then you write x p1 plus p1 plus 1 plus a, etc., x p1 plus p2 plus a. So I take now gates consisting of two groups. I take a group I take some number of gates, and then I take other points, p1 plus 1, etc., and I shift all these points. So what is the picture? The picture is the following. You have a set, just all these group points, which is some set, yeah? Now you have another group points. These are x1, etc., xp1. Now xp1 plus 1, etc., xp2 plus 1. So you have to, this set you do not move, but this set you shift up to this point. And you are about this probability. If this probability factorizes, then we say that process is ergodic. So it will be x1, etc., xp1 times p xp1 plus 1 xp1 plus p2. Okay, asymptotically, you can think about this asymptotically, that when a is big, you have an approximate factorization, and since you are allowed to write this part and this part separately, then you use homogeneity, you remove a's, and
Could
you get this one.
board a little bit upstairs?
Sorry?
Could you push the board a little bit up?
Oh, excuse me. Yeah.
Thank you.
So ergodicity is in a way a rather weak form of the decay of correlation between values of your field. If you have your fields in two quite remote domains, they almost do not feel one another. So in fact, I need even not, if it is just a limit, it is already not ergodicity, but something stronger that's known as a mixing. Ergodicity is even weaker, but nevertheless, in a certain sense, it is like that. So I repeat, the homogeneity, it is just a translation invariance, but ergodicity, it is a kind of, decay of correlations. And in particular, it's good exercise to check that if you take this example with irrational rotation, then it is homogeneous process and ergodic process. But this property is not valid. There is a weaker property. Okay, so we have, this is just a reminder of basic notions of the ergodic theory, because I'll need them.
Will we need these in this generality?
Yes. Yes. Okay, now two examples.
Let's see. Do we all understand what we've been told? Everybody who's happy, raise their hand.
Look, it is, for me, it is sufficient that for mathematicians, I see no problem to. It is just these are just definitions. You are the only objection that anybody of mathematicians could give me, that this system of definitions is not consistent. Maybe there is you found already. Please.
You have two concepts of ergodicity, right?
No, just one.
Yeah, so
The second statement.
We have to, yeah.
there's not yet a connection.
No, it's not a notion. I said how to check. It is not a notion. This is a check, and you have to prove this check. But I do not give the proof. It could be proven. No, roughly speaking, the proof is very simple. Since you have factorization, okay, since this is a question I have to answer, yeah? Okay, I have a set from sigma algebra, just this set, this cylinder now, and I make could I consider this probability especially for you? Okay, and if I have ergodicity, yes, as a tends to infinity, it is going to be this, because there is factorization, and since it is measure preserving, I'll get p square, yes?
A to infinity.
A to infinity. Oh, pardon. On the other hand, if, so here I use the ergodicity, and this is valid for any set. But now I take an invariant set. I assume that my set, if A is invariant, then this is PA for any fixed A. So we have p square equal p either 0 or 1. This means that you're okay. So I repeat, for mathematicians I see no problem, because these are just definition. If you would like to know more, take a good book on random process and you'll see everything. For physicists, I repeat, this is very simple. Homogeneity, it is just translation invariance in mean. So you have an event here, you measure something in that part of your crystal, in random system, you measure something here, and then you measure something in translated part, and the results of measurement will be the same, because the probabilities you measure it is just the, this is homogeneity, so it's translation invariance in mean. What is ergodicity? Just decay of correlations, quite reasonable property. So if you are dealing with events, you measure something in quite remote parts to mutually remote parts of your sample, there is no correlation. By the way, all the statistics, mathematical statistics, is based on that. Because in mathematical statistics, all measurements are assumed independent. But to be independent, you have to take care of. One of the ways to take care, you measure in quite remote parts of your systems. Okay. Now, but just 2 examples. The first one, it's already half given. So I have, as omega, I have one-dimensional torus. As F, I have Borel algebra here. And SP, I have just the back measure on the unit circle. ST, I said, T is irrational rotation. And we already agreed more or less that this is ergodic process. Now I take V is one periodic function on R. For example, of course, the simplest possible, just 2pt. I write t because t is just, we use x. And now I construct my ergodic process just like that. Alpha x plus omega. Okay, it's clear from what I said that it is ergodic process. And what I would like to say more. Okay, and it is known as quasi. It's a particular, very simple case, quasi-periodic function. There is more general notion of almost periodic functions, but I will not discuss. This is just. But you see, quasi-periodic functions are known since the middle of 19th century and was extensively studied in the 20th century. By the way, the founding father of the modern theory is the senior brother of Harald Bohr.
Senior brother
of Niels Bohr, Harald Bohr. And he proved the most important theorems, etc. It was initial creation of the theory, yes. And another example is different. I take as omega, don't be afraid. What does it mean? That my omegas will be just the sequences numbered, indexed by z. So I have as a space omega, I take just the collection of all possible sequences indexed by double infinite sequences. Так, okay. Omega f is generated by all the cylinders which I already introduced. So you take, what does it mean generated? you mentioned already. You take a certain amount, a certain collection of, so to say, of sets of zero level. For the debug theory, just all the intervals. And then you do all possible unions and intersections. And you'll get corresponding sigma algebra of events. So roughly speaking, our events are cylinders, but maybe large enough. Now the measure, yes? And I take as a measure of the cylinder, say, x1 from delta 1, etc., f xp from delta p, the product of j from 1 to p, f delta j. I have to pass to another. Here I can. So where f is a sigma additive measure on the line. So it's famous product measure. You see, all the values of all v are independent because the measure is product. So this is why. And what is the standard notation from probability? So my second example. This is a double infinite sequences of. So these are double infinite sequences of independent identically distributed. A standard abbreviation is IID, random variables. So we understand that since all of them identically distributed, we will have shift invariance, of course. Because if I would write here f for every j its own f, fj, it would not be homogeneous. But since all f's are the same, our process is apparently homogeneous. And if we'll try to do the proof, which I erased, yes, for p square. You remember I gave a proof that if you have an invariant set and the process is ergodic, then the invariant set, if there is decay of correlation, then the process is ergodic. And in that proof, I use the fact that when a tends to infinity, I have factorization. But here, you will have factorization on the finite stage of your limiting process, because since your two sets will be shifted to be non-intersecting, you will have factorization. So it is evident that the process is ergodic and in best possible way, because this limit, it is already achieved after if A is big enough, we have already factorization.
Why do you need double infinite sequences? Why not?
Because I would like to do shifts in both directions. And you see, let me remind you that we are about random Schrödinger. Random Schrödinger comes from disordered systems. Disordered systems, you make thermodynamic limit without walls. Otherwise, if I would consider semi-space, if I would be interested in surface phenomena, of course, but I am interested first of all in bulk phenomena. So I do the limit. Okay. And now, to finish, I have to mention two more things. Two more things. It's a ergodic theorem. Ergodic theorem is a statement which is not simple to prove, but very simple to formulate. take a measurable function, write like that, or if you don't want to do this, take a homogeneous process, ergodic process, excuse me, and this limit exists and is equal to the expectation of psi if this expectation is finite and if t is ergodic. So in fact, if you look at the proofs, there are several proofs, all of them done by great mathematicians, Birkhoff, Kolmogorov, Wiener, Hopf. You see that the main point is to prove that the limit exists. And this is very non-trivial thing to prove. But somehow intuitively we believe that the limit should exist because there is a kind of homogeneity. Therefore we expect this. Yes? And this is the ergodic theorem. And I just would like to write the theorem in a bit different. It's good things, but it comes from motivation in statistical mechanics was proven in the beginning of 30s, first time by Birkhoff, 31. Oh no, first von Neumann, but in a weaker form. And I didn't say an important things, excuse me, because here you have a function of omega, and here there is no dependence on omega. Yeah? What was the question?
Okay, so I just wanted to know where you evaluate this expectation value of psi. So
What
on
does it
any
mean?
point or
What does it? No.
There's no x here. Right now we just this is in the probability space.
Ah, okay.
X is not present because I made the limit. So we have only omega. So in general, we do not know whether this limit exists because there could be just oscillations and no definite value in infinity. But the limit exists, and since it exists, it's not hard to prove that it is equal to the expectation. Just take the expectation of both sides and you'll get. So there are two statements, assertions. First, that limit exists. The second, that limit is not random, because this limit doesn't depend on omega. Modulo, of course, probability 0. And one more point is that not all those ergodic theorem is good things, but there are many situations, in particular in random Schrödinger theory, when it is better. We would like to have a weaker statement, weaker conditions, roughly speaking. So to formulate this, let me introduce sigma n omega, just this sum, x from 0 to 1 to n, psi tx omega. Just by definition, it is just notation. So you have again a function of two variables, of integer and event, and just looking at that scheme, you can easily prove the following. Just to be precise, what did I write? M omega plus sigma n Tm omega. So by using the fact that my T is measure preserving, and by using this scheme, I can write this is the same. So it is just the sum, and so sigma is the sum, but I see this property of the sum, and my ergodic theorem now says that 1 over n sigma n m tends to the e psi, which is in fact what? It is just sigma 1 omega. So this thing is known as additive process. There is more sophisticated name called additive cocycle, but it is you need not this notion. So we have this situation, yeah. But it turns out if we will rewrite in that form, then we can easily devise a certain generalization of so let's assume now I am going to consider subadditive process. This will be sigma n omega such that we have a bit general situation. This is why subadditive. It is less than if it would be additive. It happens quite often in applications that you have a process constructed from the ergodic transformation, but satisfying just this inequality, but not the equality like that, not the sum. And nevertheless, it turns out that there is a statement like ergodic theorem that we have that 1 over n sigma nm limit exists, and it is equal to the infimum expectation of your process divided by n. It's called subadditive ergodic theorem, and its first formulation and proof was given by Kingman, who was a previous director of the Newton Institute. I am very pleased to give this theorem in the place when he was, I think, 6 or 5 years director. Okay, this is Kingman. Sometimes it's even called Kingman, but now there are many proofs. Yes?
You keep writing sigma n m, but you mean n omega probably?
Excuse me. Yeah, thanks. Okay, now we are finished with ergodic theory, and we are coming to the, you see, ergodic, now the second part, self-adjoint operator, yeah? I think I'll give the definitions then. Now, section 2. Okay, first, motivation. Let's assume that we have a, okay, motivation. View an ergodic process as multiplication operator in L2 on Z. What does it mean? You have your ergodic process, that means the function of two variables. And this is just, if you fix omega, just a function. So you define the operator V omega acting on psi by the very simple formula, yes? Now we know that since we know that what is going on with we know the characteristic property of the ergodic even homogeneous process is the following. I would like now to translate this property on the language of operator theory. And to this end, I introduce the operator UA that acts in a very simple way, just a shift. You have a function, you shift this function, now you have a new function, and this is linear operator. By the way, it is not only linear, it is unitary operator in L2Z, because it's a shift. And it is easy to check that this property translated, this property translated on the language of operator will be as follows. I'll have UA V omega UA star is V T A omega. You can easily check that it is the same. It is just rewriting of the property to be homogeneous. Now, it is even simpler to check that if you have one-dimensional Laplacian, of course it's translation invariant. It is just the fact that your operator commute with translations, yeah? Laplacian commutes, but this is not, there is no commutativity. You have to change omega, but nevertheless there is a surrogate of commutativity. So you can write, you just looking at two things that I wrote, you can say that now if you have a one-dimensional Schrödinger operator, H omega is delta plus V omega, then it will satisfy the same of course, if I would be precise, I would write the rate of precision of of all my language. Yeah. So we have. This is a simple reformulation, but it turns out that it is useful. But now, general definition. General definition. You have, let H be a Hilbert space, A omega on H is now excuse me, omega to bounded. For simplicity, I'm about bounded operators. So what does it mean? You have a function, you have a random operator. For each point of omega, you give an operator. So I can write this A on omega, yeah? So I have a random operator like here, for example, and I have one more thing, and UA, A on Z, is a irreducible representation of Z viewed as a group with respect to addition. So we know that the integer numbers, this is a group, yes? So we have this group which replaces us, this shift operator, which is evidently irreducible representation, yeah? Okay, now we say that A is ergodic if we have the same thing. We have UA, A omega, and I'm just rewriting. UA is A TA omega with an ergodic T. So it's abstract definition, but of course copied and motivated by random Schrödinger. Okay, I'm afraid that I have to stop.
You're sort of in where you want to be after the end of the fall?
No, I am back one lecture, but what I have to do?
You go behind,
Yes.
corresponding to what you are planning to do.
Yeah, just one lecture behind.
What is the risk? So what was the last thing that you were planning to discuss? What's the risk of
The proof of one-dimensional localization. Okay, I'll try to do during one lecture, but I will be very, very
quite
dense. Excuse me, I have no choice, because otherwise it has no meaning.
Okay, I think we'll have to discuss among.
No, now I'll give the plan of of the things that I would like to discuss. My next lecture, the first part, I have to give. I would like to give several properties of ergodic operators, spectral properties that comes from just this abstract definition. It is quite fast, and then, but you can't say too much because you see ergodic operators. This is in particular random Schrödinger is almost periodic potential, quasi-periodic. On the other hand, it is random potential, and we know by experience that the spectra of these two operators are quite different. But there are nevertheless several common properties that I would like to formulate. And then, to give one simple proof, then I would like to pass to Lyapunov exponent. This is the kingdom of Ilya, but I am not going to discuss the Lyapunov exponents, how do they behave, how do they are calculated, etc., etc. I would like just to give a definition and to explain you how to use the Lyapunov exponents to prove two things. First, that I would like to prove two theorems, in fact. First, if the Lyapunov exponent of my equation is positive, then my operator has no absolutely continuous spectrum with probability 1. The first. And second, if my random operator, this is valid for any V provided that Lyapunov exponent is positive. If you are trying to prove, you see that you need a factor of independence quite strong, but nevertheless, the assertion is quite general. Second assertion is like that. Assume that our equation, our potential is such that corresponding Lyapunov exponent is positive and it is IID. And the F, it was somewhere here, okay, F has a density. The potential is smoothly distributed, bounded density. Probability measure that determine the process has bounded density. Then the spectrum is pure point. This is one-dimensional localization. This is what I would like to prove, but there are some preparations that I'm afraid I will not be able to do during one lecture.
We'll have to see how to arrange for you to get to the finish line.
Okay. I think, no, in fact, after that moment, it's already not too important for me to be before Ilya and Tom. Starting from that point, it could be doing parallel even.
Okay, we'll
So,
have to see what we
but I need just one. Okay, the next lecture I repeat. First half will be general property of ergodic operators, and second half just an introduction to just definition of Lyapunov exponent and some discussion around.
As usual, the audience has the final word on the lecture. Any questions left over? Comments? Yeah, I guess this was mostly notions, and made an effort to explain the more difficult things to also to the physicists by.
Look, but as for physicists, they have to know ergodic theory from the scratch. If you study statistical mechanics, in the first pages of statistical mechanics, they explain you what is ergodic transformation, what is ergodic theorem,
But
etc.
just to translate it to
Yeah, but yes.
the essence is
Me, myself, I learned first from Landau Lifshitz all this stuff again.
this,
No.
not in this language.
Yeah, no, of course, yes.
David Bridges.
So I do have a quick question. So in your case where you considered rotation by irrational angle,
Yes.
right? And then you're not going to get the mixing property, but I
Never.
suppose that what you would get,
Never.
no, but can I guess that what you would get is that on average, in other words,
No, there is, the precise statement, the irrational rotation of the torus, one-dimensional, multidimensional, is ergodic, but not mixing.
right. So,
Nothing else. No, you have nothing except ergodicity.
but can I say the following thing? If I take my two sets and
Yes.
I translate them,
Yes.
right? If
I understand.
average,
I understand. No. Yeah, because you remember when I wrote ergodicity, I wrote in quotation marks
Yeah.
this limit.
Right.
because this is limited in Cesaro sense.
That's what I'm asking. Right.
Yeah, this is ergodicity. When you just the pointwise limit, it will be mixing. If you would like that your limit will be uniform with respect to the sets, it will be strong mixing. If the decay is exponential, it's called exponential mixing. There is a whole hierarchy of the degree of the dependence, you know. Up to in the IIDs, when you have on the finite step, you have already factorization. But in Gaussian case, everything is included in the correlation matrix, of course, as you understand. Yeah.
All right, so let's thank the speaker.